Welcome to the Explainer. Today, we're going to look at chemistry a little bit differently. Forget the idea that it's just some boring list of elements or confusing letters you have to memorize. Instead, I want you to think of chemistry as a secret code. It's literally the language of the universe just waiting to be cracked. And once you understand the rules of this language, you can read the building blocks of absolutely everything around you. To get us started, think about this. Why do we all call the stuff we drink water instead of its highly technical name, dihydrogen monoxide? I mean, dihydrogen monoxide sounds like a highly dangerous, top-secret chemical, right? But it's exactly the same thing. By the end of this explainer, you're going to understand exactly why this happens, how to decode these complex names, and even how to write them yourself. Okay, let's dive into our checklist for today's Grade 10 exam requirements. We're going to cover classifying types of matter, elements, mixtures, and compounds, decoding chemical names, special rules and ions, writing chemical formulae, and finally, mastering those exam skills.
Section 1. Classifying types of matter, the big picture.
So, before we can actually learn the words of our secret language, we've got to understand the fundamental categories of the materials we're naming. Now, what's really interesting is how we can break down all chemical structures into three main branches: ionic, covalent, and metallic. As your exam guidelines point out, literally every single chemical structure falls into one of these three buckets. Ionic structures form these giant lattices, like table salt. Covalent structures share electrons to form molecules, like water, or massive networks, like a diamond. And metallic structures, well, they create this incredible sea of electrons, just like a solid piece of copper.
Moving on to Section 2. Elements, mixtures, and compounds, the chemistry alphabet. If those chemical structures are the grammar of our language, then elements and compounds are the alphabet and the vocabulary. Think of atoms combining like building a structure out of colored balls. Elements are the individual colored balls, but when atoms of different elements attract each other through strong chemical bonds in very definite proportions, well, they form a compound. It's just like linking a red ball to two blue balls to build a specific, recognizable shape.
Now, the absolutely crucial point here is distinguishing between pure and impure substances. This is a massive requirement for your exams. Pure substances, which includes both your individual elements and your bonded compounds, are completely uniform. But if you just mix different substances together without any chemical bonding, you get an impure substance. We literally just call that a mixture. These mixtures can be homogeneous, meaning they look perfectly uniform throughout, or heterogeneous, where you can actually see and easily separate the different components using simple physical methods.
Section 3. Decoding chemical names. Nicknames versus full names.
Okay, this is where the magic really happens. We are going to translate our chemical alphabet into full sentences. I absolutely love this explanation from the Sayavula textbook. Think about what you call your friends, right? Some have a long formal name, and then they have a short, punchy nickname. Chemical substances are exactly the same way. The written-out name, like sodium chloride, is the full formal name. The chemical formula, NaCl, is the short nickname. Both describe the exact same friend, and understanding how to seamlessly switch between the two is exactly how scientists communicate efficiently. Let's see how this builds into actual rules. Rule number 1 of decoding. The element on the left side of the periodic table always gets to be named first. It's usually the metal. So in our NaCl example, sodium sits way over on the left in group 1, and chlorine is on the right. Because of that, we say sodium first, and then we change the ending of that second element to "ide," making it sodium chloride. But wait, what if we have two nonmetals bonding covalently? How do we know how many atoms of each are hiding in the nickname? Well, we use Greek prefixes. Think of these prefixes as your cheat sheet. Mono means 1, di means 2, tri is 3, tetra is 4, and penta is 5. These prefixes act like little secret tags, telling us exactly how many atoms of each element are in the molecule.
See how perfectly that translates our code from earlier? Let's take CO2. You have 1 carbon and 2 oxygens. Because there are 2 oxygen atoms, we just grab the prefix di and attach it to oxide. Carbon dioxide. Boom! It really is that straightforward.
Section 4. Special rules and ions. The advanced code.
Now, just like English has weird words that totally break the spelling rules, chemistry has a slightly more advanced code for particles that carry an electrical charge. But before we read these advanced names, we've got to define what an ion actually is. When an atom gives off or takes up electrons, it isn't neutral anymore. It gains a charge. If it loses an electron, it becomes a positive ion, which we call a cation. If it steals an electron, it becomes a negative ion called an anion.
Your unit revision materials provide the ultimate decoder ring for the exams, showing how these anions often change their ending. A single atom might end in "ide", like chloride. But if it's a polyatomic ion, which is just a fancy way of saying a group of atoms acting together, usually with oxygen, it often ends in "ite" or "ate", like sulfate or carbonate. Memorizing these common ions, that is an absolute non-negotiable step for your Paper 2 exam.
And please don't let the exceptions trip you up. First, transition metals, right in the middle of the periodic table, can form ions with different charges, so we use Roman numerals in brackets to declare their charge. Think copper 2 chloride. Second, look out for acids. They almost always announce themselves by starting with hydrogen, like HCl for hydrochloric acid. And third, bases, they typically feature a hydroxide group, which is literally just an OH tacked onto the end.
Section 5. Writing chemical formula. Reversing the process.
All right, we've learned how to read the names. Now we're going to act as the architect and write the molecular nicknames ourselves, completely from scratch. Writing a chemical formula for an ionic compound is essentially a simple three-step balancing act. Step 1, identify your positive metal cation and its charge. Step 2, identify your negative non-metal anion and its charge. And step 3, this is the most important part, combine them in a ratio so that the total positive charge and the total negative charge perfectly cancel each other out to equal 0. The final compound must be completely neutral. It's just like a puzzle.
But remember our question from the very beginning about dihydrogen monoxide? Well, just like slang in a spoken language, some covalent compounds have been around for so long that scientists gave them common, traditional names that totally ignore the strict prefix rules. H2O is water, NH3 is ammonia, CH4 is methane. These rebels don't follow the rules, so they just have to be memorized.
Section 6. Mastering your exam skills. The final checklist.
Let's tie all of these decoder skills directly back to exactly what your grade 10 examiner is going to test you on. Your CAPS Physical Sciences guidelines are incredibly specific. You are officially required to know how to write names ending in "ide", "ite", and "ate". You must be able to write formula from names using those Greek prefixes we just talked about. You need to classify substances as metals, metalloids, or nonmetals, and identify if a structure is ionic, molecular, or metallic. Basically, treat this checklist as your personal roadmap to acing your chemistry paper.
So, you're no longer just staring at a textbook trying to memorize random letters and numbers. You actually have the key to translate the chemical makeup of every single substance around you. You understand the grammar, the alphabet, and even the slang. So look around you. What are you going to decode next? Thanks for joining me on The Explainer, and keep questioning the world around you.